All right, everybody. Today I've got, by popular demand, a video on completing the square of a quadratic function. We know we can use completing the square to solve a quadratic equation. Today we're going to use it for the slightly different purpose of writing the function in vertex form. All right, so here we've got standard form, ax squared plus bx plus c. And I suppose we should say, busy, gotta go. How do we write it into vertex form? Okay, so what we're going to do is complete the square. So here's how I do it. I always rewrite the function so I've got a space for where I'm going to complete this square, where I'm going to put the missing term. Now, what is that missing term? Well, this is when we get the classic vertex form. Copy everything down, including the plus 6. Vertex form needs x plus or minus k. That thing is always going to be half of this. So there's the vertex form taking shape, x minus 2 squared. But in order for x minus 2 squared to be equal to the beginning, I had to add a 4 here. So this negative 2 squared is 4. And if I added a 4 on the right side, I gotta add it on the left side. So what I have here is, I have the vertex form, but I just need to move this 4 over to isolate the f of x. And so here we got it. Only a few lines of work. X minus 2 squared plus 2. And just for completion's sake, we can say, okay, what would the vertex of this be if we graphed it? It would be a parabola of the vertex at 2, 2. Okay, let's do the slight variation where there's 2 steps first. So in the original one, it was already in standard form, descending order. The x squared term is first, then the x to the first, then the x to the 0. Here, just remember, we do want to rearrange it so that we've got descending order. So let's put the negative x squared first, 2x next, and then plus 8. Okay, now one more difference. Here the leading coefficient was 1. Whenever the leading coefficient is not 1, the first step you need to take is to factor out that leading coefficient, but only factor it out of the first 2 terms. Do not factor it out of the constant. So notice the difference. Here we had x squared minus 4x and we left a blank and then the constant. Here we've got x squared plus negative 2x and we left a blank, but we had to factor out the negative. So it becomes negative 2x there. Okay, pretty much the same, but pay attention to what the slight difference is going to be. Now, keep the leading coefficient out here. When we get our form, vertex form, we still do that kind of stuff the same. And we still do this step the same also. We're going to divide this by 2. So it becomes negative 1. Still the same. We're going to square this so it becomes plus 1. But now when we're balancing the equation, up here we added 4, we added 4. Here when we added 1, it's really not just adding 1, it's adding 1 times that negative in front. So when I put a 1 here, I also need that negative 1 from the leading coefficient that I factored out. So really what we have here is negative 1 plus h plus h of x. So you just have to be careful when there's a leading coefficient other than 1. The rest looks pretty much the same. And that should be our final result. And our vertex is 1, 9. So of course this would be a downward opening parabola. Okay. Bonus question. How are the steps of completing the square related to the formula for the x-coordinate of a parabola's vertex? For example, to complete the square, you need to factor out the leading coefficient a. Then you need to divide by 2 to... I can explain a little bit. So, right, the idea of completing the square, whether it's to solve the equation or to just rewrite a function into vertex form, is that idea that we want this part right here, a binomial squared. when we're solving it so that at the end we can take the square root easily. When we're doing this here, it's because we know vertex form is f of x equals x minus h squared plus k. So either way, we want that binomial squared. So it should look very similar to solve, completing the square to solve. Maybe the only difference is, you got that y there instead of a 0, and you're going to have to move things back at the end. There are other ways to show this work. Like I always do the 4 on both sides, but I've seen some people will do a 4 and a negative 4, because that also goes to 0. However you slice it though, it's just about making this part a perfect square trinomial that's equal to a binomial squared. Right? You may need to watch that a couple times, but that's the long and the short of the method. How about this? A little history, free history. This is cited from the book of the maths book, for you Aussies out there, maths instead of math. What is completing the square? Well, just a little free history for you. So completing the square actually dates back thousands of years to the Babylonians. But a very important figure that you should know in math, Al-Khwarizmi, a man born in present-day Uzbekistan and who did his work in present-day Iraq and Baghdad, was very famous. You know how famous he is? He's called the father of algebra. In fact, algebra, the word in English, comes from the Arabic words that he used to write, because he wrote in the language of Arabic. What does that have to do with completing the square? Maybe you've seen this diagram. Al-Khwarizmi, was one of the people that explained how to solve this quadratic, x squared plus 10x equals 39. You could solve this using completing the square by saying we've got two terms. X squared plus 10x is like a two-term polynomial. X squared could be represented as x times x. A square whose area has x squared because it has sides x and x. 10x is added on to that. Well, then we would have a rectangle with one side x, one side 10. So x squared plus 10x is the area of this. If we want it to equal 39, we need to find what this unknown side x is. We could take this rectangle, rearrange it. The sides match up because this rectangle has side x and the square has sides x. So the area of this dark blue and light blue together equals 39. That's hard to solve. Geometrically, it's hard to solve, right? Ancient mathematicians used geometry. But Al-Khwarizmi started to use algebra to transform the geometry into algebra to make it easier to solve. And he noticed, okay, this geometrically would be easier to solve if we had a complete square. Right now, we don't. We're missing this corner. So he's asking, what do we have to add here to complete this square? Well, in this case, it's 10x divided by 2 is 5. So we need a square that has 5 and 5. So we're adding 5 squared, divide the 10 by 2, then square it to get 25. And that would complete the square. And if we add the 25 also on the constant side of the 39, then we now have this x plus 5 squared right here equals 25 plus 39 is 64. Now we can square root it. Or if this were a function like we did in the video, we could minus the 64, and we could say it's like a parabola with a vertex -5, comma, -64. There's a little history for ya. That'll do it. Make sure to leave your questions in the comments. Keep studying. Keep asking questions. And as always, go blue.